Let's just do a little walk down memory lane. Oh my goodness, look at all these words. Okay, so let's just go back a little bit and say we've learned about something called Venn diagrams, and it's a visual tool that shows how events overlap. So that was something we learned about. And then we also learned about a tree diagram. And a tree diagram is another visual tool that helps us compute probabilities for dependent events. It can also work for independent. But basically, the outcomes of each event are shown along with the probability of each outcome. So we have the outcomes at the end of the branches and then the probabilities on the branches. And that is something which we've been working on. And when you use tree diagrams, you find all the paths that contain outcomes of interest, you multiply along the path, and if there are multiple paths that are favorable, you then add them. Okay, so this is kind of what we've been up to recently. Today's lesson is going to focus on something called a two-way contingency table. And this is a very useful tool for organizing data. It also, especially when we want to determine whether two events, each with only two outcomes, are dependent or independent. So when we have a table, it's much easier for us to work out whether the two events are independent or dependent on each other using the table data and an equation that I'm going to show you later on today. So give me a thumbs up, other than the last one. Does the first, this we have to talk about, but do these first two sound familiar to you? Give me a thumbs up or a happy face if those first two things sound familiar to you. Okay. Now, the other things, as we look back on this topic, there are some other identities that we need to be familiar with. There is something called the addition rule. And so you will sometimes see that if we've got any of these things and we want to work out one of the other things in the equation, we just sub it in. So that's something just to be aware of. It's easier when you see them in an equation, but just this is for mutually exclusive events. There's something called the complementary rule. And then the one that's going to get a lot of airtime today is if we want to check if two events are independent, we look at whether the probability of A times the probability of B is the same as the probability of A and B. And you're going to see this come up a lot today. So maybe I've had a bit too much theory to start with, but I just wanted to give you a feel for the ideas that are going to come up in today's lesson. So let us go to the lesson. And all we're going to do today is we are going to start with a table. So let's have a look at this table. It says, this table gives information about the favorite sports of pupils in a year 7 class. So we have boys and girls. Those are two possible things on the horizontal. And on the vertical, we have favorite sport. So this would just be gender, in fact. Let me put that in. So this would be gender. And here we'd have favorite sport. So essentially, we're comparing these two. Oh, let me use a different color just to make it easier. And we see there are 10 boys who like football, 4 boys who like athletics, or they have it, their favorite sport is that, and somebody else has another sport. And then for girls, I want you to give me the answers for A, B, C, and D. And I want you to put them in the chat for me. And welcome to, who else has joined us? Kwande, Usasiwa, Tandiwe, welcome to Maths. It is good to be with you today. We are just simply, today is our last lesson on probability, and we are looking today at data tables and independence and things like that. So in the chat, I want to see answers for A, B, C, and D. And Just give me a thumbs up if I'm coming through clearly. I'm worried that my internet's not working properly. Are you hearing me clearly? Are you okay? Just give me a thumbs up if it's coming through okay. Okay, fantastic. So I'm just going to wait for my answers. How many boys chose athletics as their favorite sport? That's the first one. Well, let's go and look. Boys, athletics. First answer is 4. Then the next one, what's the most popular sport with boys? We look at the row with boys and we see clearly it is football. Okay, what about C? How many girls are in the class? So if I look at the row for girls, 5 plus 4 plus 7, then I'm going to add an extra total thing here. It's going to be 9. That's going to be 16. How many pupils are in the class? Well, I guess I need to see how many boys there are. So there would be 15 there. And then the grand total would be 31. But you know what I'm going to do is I'm going to show you with any table, it's very helpful to have a total column and a total row. So let's get a total row and a total column. So for 15 for that, 8 for that, 8 for that. So how many pupils are in the class? Well, 15 plus 8 plus 8 gives me 31, or 15 plus 16 gives me 31. So give me a thumbs up if you understand how I calculated the table column and how I calculated the summary column and the summary row. That you understand where the 15, 8, 8. Okay. Now, whenever students deal with tables, they often find that total row is a bit confusing. And I just wanted to do it slowly so you understand how they work. Now, I want to ask you this question. In this class, if you randomly choose someone from the class, what is the probability that they will be a boy? So if you just look at your table, if you randomly choose someone from the class, if you randomly choose someone, what's the probability they will be a boy? So we look at how many people there are in the class. There are 31. And Tamir, Bukle, Callan, Tandiwe, you've smashed it. You've said, well, look, how many boys are there? There's 15 out of 31 boys. Okay, awesome. Brilliant at that. Now, I want to ask you, what is the probability that a randomly chosen person in the class likes football? What is the probability that a randomly chosen person likes football? Well, it's still going to be out of 31. And how many people? I go to the football column and I get 15 out of 31. Well, isn't that useful? Okay, so that wasn't so bad. Also 15 out of 31. Okay, last one before I move on. What is the probability that a randomly chosen person is both a boy and likes football? So the question is slightly different now. It's saying, look, there's a randomly chosen person in the class. So I guess we could say, well, not guess, I know there's 31 people. What's the probability that there will be a boy and they like football? That randomly chosen person will be a boy and like football. So you have to actually, it's not 10. Well, no, sorry, it is 10. Okay, so it's going to be 10 because if you look at this, It's how many, it's going to be this one over here. Now, take a moment and think about that. You had 31 choices, but only 10 of them would be a boy and would like football. So you had to go and get that 10 there and say the probability of a randomly chosen person being a boy and liking football is 10 out of 31. Give me a thumbs up if you followed that. Now, if we want to check whether these two things, if sport is independent of gender, right? If there's no, all we have to do, and this is going to seem weird, but we're just going to do it now, is we're going to check, look, what is the probability of someone being a boy in this group times the probability that they like football? Can someone work that out for me? How would I do that? I'd go 15 over 31 times 15 over 31. What am I going to get in decimal land? I'm going to take out my calculator too, and we're going to check. 15, so fraction 15 over 31 times 15 over 31. And in decimal land, I get 0.2341, blah, blah, blah. Yes, Buchle, let's go to you. I see a question. What is your question?
So I have a question.
Yeah.
Do we generalize the people that like football? So we're also including the girls that like football. That's why we're using 15.
Yes. Yeah. So
So
that's what we're doing at this stage. And I'm just teaching you this equation. You'll see later in the lesson how it connects up. So that is the probability of that. Now, what is, if I put it into decimal, what is the probability of being a boy and liking football? That's 10 out of 31. So let's just quickly work that out as a decimal. Okay, this is 0.3225. Now, the main thing I want to draw your attention to is that this is not the same as this. And so basically we would say the probability, this thing times this thing is not the same as this. And that's going to sound a bit weird at first, but you don't have to think too far. Are we all happy that based on what we just worked out, that these two are not the same? That's all I want you to check. That's it. If you can see that they're not the same, that's all you need to know. Everyone? Can I give me a thumbs down if you don't understand? But can you understand that these two are not the same? Okay, now, this is how we check for independence. So let me show you the definition. And then we're going to do another example where you're going to fly a bit more solo. Remember, when events are independent, we can work out the probability that they both occur by multiplying the probabilities. So this is not what we're doing now. This is actually when they say these events are independent. If they're independent, you can use this formula. But we can also use this rule to determine whether or not events are independent. So if you check, and what I did now is I checked whether the one times the other was the same as both of them at the same time, essentially. And because they were not equal, they're not independent. Now, that sounds weird in a formula, and it's much easier if you see it in an example. But again, I want to ask, can you sort of see some connection between that and what I was doing above? So all I want to know is, can you see a little bit of a connection between this and the first example? Can you see like we're multiplying one thing by the other, and then it has to be, okay, so you've got me so far. All right, let's go and test for independence. So here is a table, and all the table has is it has a hair color of 50 learners were recorded. Now, what's really nice about this table is that it has total columns built in. So all I want you to do first of all is get familiar. So again, we have on this thing we have gender, and over here we have hair color, right? So those are the two different events. Can you give me the answers over here for 1, 2, 3, and 4 by looking at the table? Let's just do that first. Let's just do that first. And once you have told me, calculate the probability that a learner chosen at random will have brown hair. Well, I'll do number 1 with you. There are 50 students in total. How many of them have brown hair? 17 out of 50. Or you could say there's a 34% chance a randomly chosen person will have brown hair. Tandiwe, you are on the money. Okay. You're going to do the rest of these for me. So we've done number 1. What about number 2? Well, number 2, blonde hair. So a randomly chosen person, there are 50 people in this survey. How many of them are blonde? Blonde. 11. Okay, so we've done this one. Now, what about this? We'll have black hair or brown hair. Ooh. Still out of 50. What's this going to be? Black or brown. That means either of the two. So where's black? Black is 22. Brown is 17. So actually, it's a favorable outcome. There's a 39 out of 50 chance you will get someone with black or brown hair. So it's very likely you'll get someone with black or brown hair, or another way of saying that, yeah, is someone who's not blonde. Okay. And you could also write this as 78%, or 22%. It just depends on what the question is asking for. Okay, what about number 4? What about number 4? We'll have blonde hair or brown hair or black hair. What's that going to be? Well, if all 3 of these are favorable outcome, you have to get in the sample, there are only people with black, brown, or blonde hair. So there's a 100% chance you will get someone, if you're randomly choosing from the sample, of that. Give me a thumbs up if this table makes sense to you, so far, anyway. All right, now that you've learned how to read tables, and I can literally feel your brains growing through the internet, and you are getting good with tables. Now, let's check. Do we think, is gender or is hair color independent of gender? So we've got hair color over here, and we've got gender over here. So what we're asking is, look, does it matter if are you more likely to be blonde or black-haired or brown-haired, depending on your gender? We're trying to work out, is there a link between these two? So remember, we have this thing, if the probability of A times the probability of B is equal to that, then they are independent. But the thing is, it's not obvious how we connect these two together. So what I'm going to help you do is do that. I'm going to say, what is the probability that a randomly chosen person has brown, no, not brown, let's go with black hair. What is the probability in the sample that a randomly chosen person has black hair? Work that out for me. So you look at your table and you say, look, what is the probability that a randomly chosen person has black hair in this group? So I'm looking in the black hair part of town, and there are 50 people in this group. So there are 22 out of 50, or there's a 44% chance. Now, if I look at this equation, I have two different things, but they actually have to come from the two different events on the sort of the side and the top of the table. So I'm not going to ask about hair color here. I'm going to say, what is the probability in this data set that a randomly chosen person is a girl? Notice how I'm choosing from a different event here. Okay. Tell me what you get for that. So if I look at the column with girls, I say there are 24 out of 50 girls. Okay, now, if you think of this equation as being our guiding process, you can kind of see that my next step is going to be to say, look, take the probability of having black hair times the probability of being a girl. But now I've got only two parts of this equation. There's one more part that I need to work out, and it needs to be based on what I chose here. And what I'm going to work out is, what is the probability of having black hair and being a girl? Now, can you see the connection before I even compute that? In fact, maybe I should even do it below here. So let me zoom in a little bit so we have a bit more space. And I'm going to write this at the bottom where it's logically. I need to work out what is the probability of having black hair and being a girl. And I want you to look at the table and tell me, what do you think that probability is going to be? So it's still going to be out of 50, but now I have to go and look. Which part of town am I going to look in? Well, it's the girl part here and the black hair part there. It's going to be 10 out of 50. Now, what do you think I need to still do to check for independence? What do I need to check? I need to check whether or not this times this is the same as this. Okay, well, let's do that. So let's go the probability, or let's just do, we've got them right here. We'll go 22 over 50 times 24 over 50. What does that give me in decimal land? Let's do it together. 22 over 50 times 24 over 50. I'm getting 0.2112. Callan agrees with me. Now, here's the thing, guys. Don't round off with this type of calculation. You want to have a few more decimal places there, because checking whether they're equal, they either have to be exactly equal or incredibly close. So you need a few more decimals to make sure that you're in the right part of town. Okay, now, over here, if we look at what the probability for the blue one is, this is going to be so 10 over 50, I think I know this one in my head, it's going to be 0.20. Now, this is one of those ones, even though they're close, they're not the same. And so we would say the probability of having black hair times the probability of being a girl is not the same as this. And we can say, therefore, they are not independent. Oh, did I spell that right? They are not independent. So there is some relationship between gender and hair color, for whatever reason, in this particular sample. Now, I think I need to just slow down for a second and go over some important ideas. Sometimes people will say, does it matter if I chose boys instead of girls? It doesn't. But if you choose boys over here, so over here when I chose girls, I had to go to the table and look at where the girls were. If I chose boys here, then in the second part here, it would have had to have been black and boys. And the same goes for hair color. If I had chosen a different hair color, it's fine. But then when I worked out this, it would have had to relate back to this thing originally. Give me a thumbs up if you followed what I was doing there. Give me a thumbs down if you didn't. So even if you didn't get it, don't worry. We're going to take an exercise break now, and we're going to do another example like this. And I promise you, by the end, this is going to be the easiest marks you ever got. So yeah, let's just take a quick little energy break. So if you need to, take a screenshot of the screen if you want, although the recording will be available by tomorrow. And then we're going to step away from our PCs just for a second, or our phones, because our brains need to recover. Sometimes, like I say to my students in class, you've got to give your brain time to go save as. You know, the computer needs a moment to just save what you've been doing. Same thing with your brain. So let's just do a bit of breathing. So let's 3 deep breaths. Breathe in. And then one more. And then shake your arms out to get them nice and loose. Shake out this arm. Shake out the legs. And oh, it feels so good to just shake out a bit. Then we are going to do 15 jumping jacks. You know the drill for a jumping jack. It just looks like that. This will get the blood pumping. And we go in 3, 2, 1. Let's go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I can feel that I played tennis today. Sure. All right. Let us get back to our mathematics. And let's put some emoticons on screen here. Let us hit your favorite ones or how you are feeling. Let's just express ourselves for a second. Amokalang Tandiwe, I see you. Akonde, hang in there. We can do it. We will get you over the finish line, I promise. Okay, here is a question from a past exam. So let's have a quick look. 80 learners in grade 11 were asked whether they played sport for their school, and the results were recorded in the table. So it did say 80, and what's good is I can see there's an 80 in my table. So what I want you to do is tell me the answer for A. What is the probability? Actually, you know what? You can do A and B and C for me. Go for it. By yourself, lock those answers into the chat when you can. I think you guys can handle A, B, and C by yourself. So it's definitely out of 80. Female, okay, hold on. The probability of being female here is going to be 50 out of 80, because that's where, if you look at the female column, that's where the total is. What's the probability that a randomly chosen person plays sport? That's the next one. Well, it would be 48 out of 80. What's the probability that someone will be female and play sport in this sample of grade 11s? Well, it's still out of 80. What's that magic number going to be? So I look for female and I look for play sport, and the number of people who would be favorable for this question would be 21 out of 80. Okay, now that makes sense. Give me a thumbs up if you're with me so far. Are we okay for that? All right, that's good. Now I want you to work out what D is, and then I want you to tell me, are these is playing sport independent of gender? Like, if you know someone plays sport, do you know whether they're more likely to be male or female based on this data? Go ahead and try and calculate that. So that was the first one, 50 out of 80. Play sport was 48 out of 80. Now, what's that as a decimal? I'm getting 0.375. Now, for this one, for C, what is 21 out of 80? It's 0.2625. So is playing sport and gender independent of each other? Yes or no? What do you think? So for me, the probability of being female and the probability of playing sport is not the same as being female, as the probability of being female and playing sport. So therefore, events are not independent based on this data. It is just based on this data set. These two numbers would have had to have been the same or extremely close for that to work. Okay, give me a score out of 10 for how Machadiso doesn't get it. So don't worry, Machadiso, we're going to do another example now. All that we're doing, so I'm going to go back for a second. Let me go back to my definitional equation. All that I'm doing when I want to check whether events are independent is I'm really just taking, so there's the two things, A and B. But in a lot of these, like A has been hair color and B has been gender, right? And I just choose something in the data set and check whether this times this is the same as this. Now, this is a definitional formula that I'm applying, but the skill of today's lesson is understanding how to take this idea and apply it to table data. And so that's why I want you to look carefully in the next example, how I almost do those steps again. So can you give me, before I move on, can you give me a score out of 10 for how you're feeling about independence calculations and table data calculations so far? And then we'll do another example. I just want a score out of 10. 10 is perfect. 0 is nothing. 5 is okay, but needs to get better. How are you feeling so far? Now, what will happen probably in your tests is they won't always give you all the table data. You'll sometimes have to work out your table data. And then things like, actually, do I want to do this one? Let's have a look. Maybe I can do, let's find something like this. Okay, let's do this one. Let's do this one. So it says, a survey is done at a local shopping mall to see the number of males and females that have broken an arm in the last year, right? So we're looking at gender versus breaking an arm or not breaking an arm. Now, just off the top of my head, part of me thinks this may not be independent because, but again, I don't know. You have to look at the data. But generally speaking, males tend to take more risks, I don't know, than females from what I've observed. So part of me thinks, I don't know where this is going, but part of me thinks it might not be independent, but let's see. Let's see what the data says. So can you work out for me the values of A, B, C, and D? Tell me in the chat what you think the values of A, B, C, and D are. Welcome, Tender. So for A, it's going to have to be 140. Yeah. What is B going to be? So this was 140. Oh, I know how to do this. Look, 225. If I take away 145, 225 minus 145, what's left will be B. So that will be 80. Well, then C must just be this plus this, which is 290. So that's all good. And D is also just going to be adding the two together. So D is going to be 285. So you know what? Actually, this would be such an interesting project. Imagine if you literally did this. You would get a real sense of, and it's sort of, this is sort of similar to car crashes. If you think about it, like if you guys aren't probably old enough yet to know this, but your gender does affect the cost of your insurance for cars. And I'm guessing that's because accident rates are probably higher for one gender than another. And I don't know which one is which, but I suspect this idea comes across in insurance as well. Anyway, let's keep going. So it says here, what is the probability that a person chosen at random is a female who has not broken an arm? So this question is a bit more detailed. Can you tell me the answer? What is the probability that a person chosen at random is a female who has not broken an arm? What would your answer for 10.2 be? And I'm deliberately not going to say too much. I'm going to let you fly solo. I'll highlight some key words, but I think 575 is an important number, but what is going to go above that? So female is here, did not break an arm. So this is the group of people who were female and did not break an arm. So it's 145 over 575. Okay, well, that makes sense. Now that I got into the data, I feel like I understand where that came from. Okay, now, next question, 10.3. Given that a male shopper is questioned, oh, this is important. It's no longer a randomly chosen person, given that a male shopper is questioned. So how many people are we questioning now? What's going to be at the bottom here? In some senses, there's a condition here. The condition is the person must be male. If I look at my table of data, how many males are there? There are 350. Look how useful the table data. Like you can so easily get what you need quickly with the table. Okay, so we know there's 350 people. Of those 350, what is the probability that person has broken their arm? But again, we're living in male land here. Okay, Bukle, let's go to your question. Yes, how can I help?
So aren't we using the entire sample, entire sample size? Why is it saying 350?
No, because it's really important that the question says, given that a male shopper is questioned. So now it's conditional on that statement. We're only considering the male people in the sample, and the number of male people is 350.
Oh, okay.
Does that make sense now? But it's a good
Yes,
question. But it's all about this condition here. Okay. What's going to be here inside the 350? So male broken arm 210. There we go. 10.3. Okay, now it says determine using appropriate calculations whether or not breaking an arm and being male are independent. So they've told me I need to work out what is the probability of being male, what is the probability of breaking an arm with no restrictions, and I also need to work out what is the probability of being male and, well, let me put and the word, not the symbol, and breaking an arm. And before I even work that out, can you see the connection? Give me a thumbs up if you see the connection between the three things I'm looking for and the fact that I'm trying to check if they're independent. Can you see that skill, that process? Give me a thumbs up if you see it. Give me a thumbs down if you don't. All right, now I want you to work out what is the probability of being male in this particular question, given the sample that we have. So again, there's no restriction here, hey? It's probability of being male. So what's the number at the bottom going to be? What's the number at the top going to be? We're back out of 575. And now at the top, we're going to have 350. That actually makes sense. Now, what is the probability of someone in the sample breaking their arm? So again, because we're looking at the whole sample, it's 575, and breaking an arm is going to be 290 out of 75. Okay, now, what is the probability? Well, we know this is still going to be out of 575, but what is the probability that you choose someone who's male and they've broken an arm? So I go for male, broken arm. It's going to be 210. Okay, now we need to check for independence. So what I'm going to do is I'm going to work out what this times this is, which is basically just multiplying these two. So let's see what I get. In fact, you do it, and you tell me if you think these events are independent. I'll give you a chance to do this while I do it as well. And it's quite nice to put it in decimal because it's so much easier to compare decimals. And I'm going to put a couple of decimal things just so that I can really see how close they are. Now, that was the part where I multiplied the two. Now, what is 290 over 575 as a decimal? Well, let's find out. 290. Sorry, I lied. 210. I need 210. I had an old person moment. 210 over 575. And I get 0.365217. Da, da, da. All right. So again, now it is possible that they can be the same sometime, but in this situation, therefore, events are independent because these two are not equal. And I should actually write a little sentence here. I should say, this is not equal to the probability of male and break. Give me a second. Oh, break arm. And we're going to do one more question, and then we're going to finish for tonight. But let me just. Sorry, I told a lie, and I know why. Events are not independent. Another old person moment, guys. I'm aging in front of your eyes. Maybe I should have done more jumping jacks. Not independent. Okay, can I have a quick logic check? Are we all happy? Thumbs up if you understand my example. All right, good, fantastic, fantastic, fantastic. All right, one last question. Let's see. Now, this is interesting. What I will give you is they are mixing and matching two parts of town here. Now, earlier in the lesson, I told you about a probability identity, which said the probability of A plus the probability of B. Okay, let me write it out like this. The probability of A or B is the same as the probability of A plus the probability plus minus the probability of A and B. And this is a universal identity that you can use. Now, I want you to first work out, given what they've given you here, can you work out the probability of A and B? Now, I'm giving you a bit of a hint by giving you that formula above, but can you connect these two worlds? See if you can do it. And then we'll just do this last one, and then we're done for today. Now, I want probability A and B. So that's what I want. What do I have is the question. See if you can use what you've got here to help you work out what the probability of A and B. What do you think I should do? Give me some tips. Give me some tips. What should I do first? Who can help me? Tandiwe, can you help me? I feel like I need someone to help me get started. What would you do? I've got these numbers here. It's somehow connected to this. Tandiwe, you have saved the day. Fantastic. Take these values and put them into the formula. So that's 0.2, that's 0.5, and this is the OR part. This is 0.6. Now, can you move things around? Well, I think I'm going to move this one, the P, A and B to the one side. But when I do that, I need to move this to this side. So what are we going to get as our answer? Okay, 0.1, or we could say it as 10%. Perfect. Okay, so now here's the thing. We have to check, are the events A and B independent? So I will ask you this. Well, actually, no, I don't want to give it away. You tell me, are they independent or are they not? Use what you have learned over the lesson to help you reason your way through this. So to check for independence, the definition says, is the probability of A times the probability of B the same as something? So I guess I should go 0.2 times 0.5. And what do I get? I get 1 over 10 or 0.1. So, are the events A and B independent? Yes, they are, ladies and gentlemen. Yes, they are. So they are in A and B are independent because the probability of A times the probability of B is equal to that. And with that, I dropped the mic or the pen, literally, and I called it a day for today. Now, just to go over, today's lesson was about understanding data in tables. It was about understanding how to check for independence. And it was also about how do I connect other identities to this independence idea.